Good morning. Today we'll continue the nuclear chemistry class. Okay. Under that, we'll discuss about the parts of nuclear reactors and working of nuclear reactors. Okay. So the nuclear reactor is the one. It is a device where the controlled nuclear fission reaction is conducted. Okay. So fission reactions, nuclear fission reactions, you are well familiar. For example, when uranium-235 it is made to bombard with the slow moving neutrons, say it undergoes fission reaction and produces say neutrons, three neutrons and a tremendous amount of energy, and then along with lighter particles. Is it? You have seen. Say the same principle or the reaction is conducted in nuclear reactors. Okay. Say the nuclear reactors, it is mainly made up of, or its parts will be divided mainly into five parts. First one is nuclear core or fuel rods. The second one is moderator. The third one is control rods. Fourth one is coolant. And the fifth one is shielding. Okay. See the first one, nuclear core. Okay. Or the fuel rods. Usually here fissionable materials like uranium-235, uranium-238 or plutonium-239 are taken in the form of cylindrical rods, okay, which are arranged systematically in the nuclear core or in the chamber, inside chamber, okay. So now they are the very good fissionable materials which liberates a tremendous amount of energy, okay. So with this, we'll move on to the next one, that is the moderator. See, in the nuclear reaction, when the uranium-235 is used, so the slow-moving neutrons are needed to bring the, say, efficiency in the reaction. That means slow-moving neutrons are easily absorbed by the uranium-235 and which leads to the fission reaction than the fast-moving reaction. See, the abundance of uranium-235 is very less. In nature, it is only 0.7%, and maximum abundance of uranium-238 is more. Therefore, while taking the uranium-235 as a fuel rod or as a fuel in the nuclear reactor, uranium-238 is also taken along with uranium-235. Okay. Now, it will be made in the form of rods, and when the one uranium-235 undergoes fission, it produces three neutrons with liberation of energy. Okay, and now such liberated neutrons are very fast. Okay, they are highly energetic and they are very fast moving neutrons. And usually the fast moving neutrons are readily absorbed by uranium-238, which is less fissionable, and slow moving neutrons are readily absorbed by uranium-235, which is more fissionable. Are you clear? Therefore, it is necessary to slow down the speed of neutrons. In order to do so, moderator is used. And moderators like ordinary water or heavy water or graphite, solid graphite is used as a moderator. And when the fast moving neutrons are liberated in the fission reaction, they will be made to undergo drastic collisions with the molecules of moderators. Thereby in each collision, they loses energy. See, when they undergo number of collisions, there will be a transference, the energy will be transferred to the moderate molecules, to the molecules of moderator, and thereby the energy of neutron will decrease and thereby the speed will be decreased. That means the fast moving neutrons will be converted into slow moving neutrons by drastic collisions with the molecules of moderator. Therefore, the job of moderator is mainly to slow down the speed of neutrons. because slow neutrons are needed than the fast moving neutrons in order to make uranium 235 to undergo fission reaction than uranium 238, which is less efficient. Okay, now say if the ordinary water or deuterium water, that means heavy water, is used as a moderator, then that reactor is said to be a swimming pool reactor. That means when the moderator is either ordinary water or heavy water, then that reactor is said to be a swimming pool reactor. If the solid graphite is used as a moderator, then it is said to be a atomic pile. That reactor is said to be a atomic pile. Very clear? Okay, with this we'll go to the next one, control rods. You are well familiar, fission reactions are self-sustained chain reactions. In each step, there is a liberation of tremendous amount of energy, isn't it? If it is not controlled, it leads to explosion, is it? So now the same thing happened in the Chernobyl of Ukraine in 1986, where uncontrolled chain reaction led to, say, explosion, is it? So now, in order to control the in order to control the fission reaction, say, the use of control rods is necessary. And the control rods, usually they are made up of materials like boron, cadmium, silver, hafnium or indium, okay, which has got very good absorbing nature of absorbing neutrons, very good tendency of absorbing neutrons. Thereby the number of neutrons will be decreased, and as a result the fission reaction will come under control. That means three neutrons are liberated in each fission, and out of three only one is needed to continue the reaction or to maintain K is equal to 1, and two more are to be removed, and those are removed means they are made to absorb by these control rods. Okay, so control rods, job of control rods is they absorbs extra neutrons. They absorbs extra neutrons, thereby reducing the number of neutrons, which leads to controlled nuclear reactions or fission reactions, where the factor K, multiplication factor K is equal to 1. So here it maintains K equal to 1. And now if the K is greater than 1, it leads to explosion. Therefore it should be steady and slow, and that is possible only when K is equal to 1. So sometimes the reaction is to be stopped or to shut down, okay, either under normal conditions or under emergency. Then these control rods are very necessary. When they are inserted to the maximum extent, then the neutrons will be absorbed. Whatever the neutrons are liberated during the fission reactions, they will be completely absorbed by the, say, control rods or safety rods, and thereby the reaction will be stopped, or say it will be closed. Okay, so now with this we'll go for the next one, that is coolant. See, in this reaction core, okay, nuclear fission reaction will be conducted, and as a result in each step there is a tremendous amount of energy is liberated, and that energy is a thermal energy, heat energy. And now around this core, say, the coolant is circulated. So the coolant is circulated in this fashion. Okay, so the coolant, usually a, say, heavy water or ordinary water, okay, or sometimes liquid metals are used as a coolants. See, when they circulate through this core, okay, they gets heated, and that hot coolant will enter this heat exchanger. So this is a chamber where the cold water is circulated, and now this hot coolant which comes out from the core, it enters this heat exchanger, and this pipe is very hot, and this water which circulated or surrounding that pipe, that water gets heated and starts boiling, and high pressure steam will be liberated, which is under high pressure. Say it enters the turbine, so thereby it will run the turbine, and to which electric generator is coupled, and here electricity will be generated. Okay, so now whatever the heat liberated here, that will be absorbed by the coolant will be circulating like this. Okay, from here hot coolant will enter, and from here cold coolant will enter. So okay, this will be circulating, and that hot coolant through this pipe, when it passes through this chamber, say the water, which is this chamber is filled with water, that water gets hot, starts boiling, and steam will be formed, and that steam will comes out here, and it enters the turbine. When the turbine starts working, say, which is coupled with the electric generator, electricity will be generated. The low pressure steam will comes out from this chamber, and it enters the condenser, where it will cool down, and cold water is circulated here, and once again it enters the, say, heat exchange. Okay, so like this the water will circulate like this, where the steam is utilized in the generation of electricity, and here the heat is generated, and that heat is taken out through this coolant, and that coolant will be circulating continuously. Okay, so now coolant, which is taken in a, say, heat exchanger, and it generates steam, and thereby the turbine will start working, and electricity will be generated. Okay, so the last one is very important, it is shielding. So shielding is the one which protects the environment from hazardous radiations. So during the nuclear reactions which is taking place inside the nuclear core, during the fission reactions, there is a number of hazardous radiations are coming out. They are emitted out during the fission reactions, such as alpha, beta, positrons, gamma radiations, etc. So those radiations are harmful to the human beings or to the environment. So in order to protect the environment, this core should be shielded well. That means it should be well shielded in order to prevent the outcoming radiations, or in order to protect the environment from such hazardous radiations. So thereby the shielding, it is usually very thick, of the length say 2 to 2.5 meter, thick concrete wall. It is a concrete wall, and inner side of the concrete wall is lined with lead. There is a lining which is made up of lead, and in order to protect the environment from the hazardous radiations, shielding is necessary. Okay, so with this I think you are well familiar with the parts of nuclear reactor, and as well as working of nuclear reactor, is it? See, the nuclear reactor mainly made up of 5 parts, and here main aim is what? The liberated heat energy or thermal energy is converted into electrical energy, which can be used further for peaceful purposes, is it? Or useful purposes. See, it is mainly made up of 5 parts. One is the reactor core or the nuclear fuel rods. Second one is moderator. Moderator is inside the core itself. The third one is control rods. So okay, these are the control rods. And the fourth one is coolant, and the fifth one is, say, it is a shielding. Okay, and the fuel rods, usually they are made up of uranium 235 along with uranium 238 or plutonium 239, then which are very good fissionable materials. The second one is moderator, which will slow down the fast moving neutrons into slow moving neutrons, isn't it? And which are able or capable, or it is they are necessary to bring the fission with uranium 235 fuel. So either water or heavy water or salt graphites are used as a moderator. The third one is control rods. Controlling the fission reaction is very necessary, okay, to avoid the explosion. And in order to do so, control rods are very important where they reduce the number of neutrons. And you have seen in each fission, 3 neutrons are liberated. So, okay, and 3 neutrons are more. We need only 1 neutron in each step to be utilized for further fission. And the 2 more neutrons are made to be absorbed by the materials, and they are like boron, cadmium, hafnium, indium, or say silver, which are very good absorber of neutrons. So these materials are used in the form of control rods, and by inserting the control rods, so okay, from the top, inserting the control rods, see, the reaction can be controlled. The reaction can be controlled. And sometimes, say, to maintain the steady and slow reactions in the required manner, K must be equal to 1. You are knowing the factor K. It is known as multiplication factor, or say it is a constant. It is the ratio between number of neutrons liberated divided by number of fissions, number of fissioning neutrons. Okay. So now if the K is equal to 1, then the reaction will be under controlled state. If the reaction is greater, if the K value is greater than 1, it leads to explosion. And if K is less than 1, so it should be made, sometimes should be made less than 1 to during the shutdown of the reaction, or to stop the reactions under normal or emergency conditions. Say control rods are inserted or the safety rods are inserted to stop the nuclear fission reaction. Okay, so now the last one is shielding. Shielding is also very important to protect the environment from hazardous or the emission of dangerous radiations during the nuclear fission reactions. Okay, so with this we'll continue in the next class. Thank you.